Welcome back. Let's do another Thevenin equivalent, but this time let's use some different methodology. So we're trying to find the Thevenin equivalent, which basically breaks down into two steps. We want to find V sub Thevenin and we want to find R sub Thevenin. This time we're going to use mesh current method mostly, with some other tricks to find V Thevenin. And to find R Thevenin, we're going to use the short circuit method. All right, the circuit that we're given has a couple of these dependent sources, and they reference each other, or they reference each half of the circuit references each other. So we've got this reference current V2, and the terminals AB are terminals of interest that we're doing the Thevenin equivalent circuit for, hanging off of here. So basically V Thevenin is between A and B, which happens to be what V2, this reference current, is also between there. So basically V2 equals V Thevenin for this particular circuit. They're the same thing. They're the same value. So we've got a 50 kilo ohm circuit, or a resistor, with V2 volts across it. And this diamond over here is a dependent voltage source given by 4 times 10 to the minus 5 V2. So it's monitoring this reference voltage over here and putting out a corresponding or a proportional voltage. Very small, 4 times 10 to the minus 5 times smaller than V2, but anyway. Okay, I've got a resistor here and another resistor here, and then a current source over here. So this is a 500 microamp current source, and then a 100 ohm resistor and a 1310 ohm resistor, kind of a weird value. And these guys share a common ground. These two halves of the circuit share a common ground, which isn't really that big of a deal, but there it is. Okay, this guy is a dependent current source, and it has the value 80 I sub B, and I sub B is the current through this resistor over here. Okay, so you've got two halves of the circuit, and they're each kind of monitoring the other, right? So this current source is monitoring this reference current I sub B and putting out 80 times that current down this way. And this guy, this voltage source, is monitoring this V2 over here and putting out a proportional voltage. So they're both monitoring each other. Now the fact that they share a common ground is really sort of doesn't matter. It's beside the point. Like, these guys are behaving independently, even though they share a common ground. You could remove this common ground and they would still behave the same. If you want an analogy for that, think about in your house when you plug in things into your household outlets. They all have a common ground. You know, the negative terminal in your house all goes to the same point. It all goes to a ground point. So the fact that things have a common ground is, they still behave as independent circuits. And you could even remove this, and that would be like a floating ground, that each one would be, have an independent ground. And that's like something like your phone, which you're walking around with. It's in the air, If you hold it in the air in your fingers, it's not grounded to anything. It's just floating ground. And a car is the same thing. A car has a floating ground because it has rubber tires. So it doesn't even matter. Like, if there were a wire across the top, well, then you'd have one circuit. That would be totally different. But when they only have one wire, you really have independent circuits that are behaving independently. And you could remove this wire and they would still behave independently. If it wasn't for the fact that these guys referenced each other's, here we're referencing a voltage on this being used on this side, and here we're referencing a current being used on this side. If If it wasn't for that, they would be two totally, completely different circuits. All right. So there's two steps to this. We're going to find Thevenin, and it turns out that we can use mesh current mostly. So that's the first step to this. We're going to find Thevenin. And then that's going to be a big problem. And then when we're done with that, we'll start over and find R sub Thevenin. All right. Well, look at this thing. If we had I beta, if we knew what I beta is, we could get this current. And then that current's going around here. That's the only current going through this resistor. So if we had I beta, we'd have this current. And then we have this resistance, so we could find the voltage here by Ohm's law. So if we had I beta, we could find this voltage, which is basically V Thevenin. But in order to get I beta, we have to look over here, and then so we're going to need, in order to get I beta, we're going to need this voltage on here, which this guy references V2 over here. So this guy references this, and this guy references that. We have to sort of work both sides of the problem at the same time. It's that's just the nature of this thing. So let's look at this. So what I'm trying to say is we need to get V Thevenin, which is the same as V2. And if we had I beta, we could get that. So by Ohm's law, let's just write an equation for that and see what that says. So by Ohm's law, V2 is just minus 80 I beta times 50,000. It's just, this is I, this is R by Ohm's law. So this would come around this way, and I beta would generate a voltage drop. Or let's see, this would, yes, I beta, or this 80 I beta, the current is 80 I beta, would generate a voltage with a positive sign here and a negative sign here. Now that's opposite the signs that are given, so we need to insert this. So that's another weirdness. So this guy basically comes from the fact that the voltage drop that's generated by the actual current direction is opposite of our reference. So this is to correct for the V2 reference current, voltage polarity. We just have to correct for it because 80 I beta is going from the bottom to the top through here, which would generate a plus minus polarity, which is opposite of what we have labeled. So that's just a little weirdness that you have to correct for. So there's that. So what is that? That we could simplify a little bit. That's going to be minus 40 with what? 1, 2, 3, 6 zeros. I beta, the big old one. 1, 2, 3, 4, 5, and then 6. Yep. So this is V Thevenin. So we have that. We can't really do any more with that. We have to kind of go over here and try and get I beta, because if we had I beta, we could get V Thevenin. So we go over to the other side and look at this guy. Let's try and on this side we've got I beta and some of the things. Let's try and get rid of this V2 by expressing V2 in terms of I beta, which we've already done. So let's do this. Let's express this thing in terms of I beta. IB rather, sorry. So basically 4 times 10 to the minus 5th V2, this thing is, and we have an expression for V2 up here, is 4 times 10 to the minus 5th minus 4 with 6 zeros I beta. That ends up being minus 160 IB. I keep saying beta, sorry about that. Okay, that just lets us deal with just I beta on the left. All right, now we can use mesh current on the left. So I'm going to go ahead and redraw that little circuit just so that it doesn't get too messy up along the top. I'm just dealing with the left-hand side as its own independent circuit because that's the way they behave. So we have a I beta loop going around here. We're doing mesh current. So there's IB loop, and on this side we've got a loop which we could call, we already know the current, so we'll just call this 500 microamp instead of using a variable name for this because we already know what it is. So we have these two mesh current loops. This is 1310 ohms, this is 100 ohms. Okay, we can write a mesh current equation for loop IB, sorry, there I go again. So you go around this loop here and you do the resistors, right? You're gonna do 1310 IB plus 100 IB. These are the IB effects. Then you throw in the total voltage here, right, which is, you're coming in the positive terminal, so it's positive, but the quantity is minus 160 I beta B, sorry. And then you got to apply superposition. You got to look at the voltage effects due to this 500 microamp current. All right, so that's going to be it's going to be 500 times 10 to the minus 6 times 100. This is the superposition. This is the voltage effects due to the other mesh current, the other loop. And this is going to have a negative sign because the mesh currents disagree. The mesh current directions disagree. Okay, and those sum to 0. So that's mesh current. You go around here, you do RIB and then RIB. That's these two guys. This is a voltage source, so you throw in the entire voltage, and you're coming in the positive terminal, so it's positive. And then you apply superposition on the shared element, the shared 100 ohm element. So the only unknown in this thing is I sub beta. So if you calculate this out, you're gonna get IB, sorry, I keep saying I beta, sorry about that. You're gonna get IB equals 40 microamps. Therefore, back to this guy, right? Therefore, V sub Thevenin is it's minus 40, 0, 0, 0, 0, 0, 0, that many zeros times 40 times 10 to the minus 6 amps. It's going to be minus 160 volts. That's V sub Thevenin. Answer. Okay, kind of a mess, but that's what you got to do. You got to sort of work both halves of this problem at the same time, and a little bit of luck helps. Let's do method 2 here. We're going to use the short circuit method to solve for R sub Thevenin. So it'll be a short circuit method. Okay, short circuit method is a method that you can use when you have dependent sources, diamonds. Okay, and for the method here, you leave the circles, you leave them on there. That is, you leave the independent sources, and then you short out across terminals AB. You short it. And when you do that, when you short across AB, you're going to get a short circuit current called I sub SC. And R sub Thevenin is going to be given by V sub Thevenin over I sub short circuit. That's the method. So I'm going to redraw both halves of this circuit over here with this thing shorted out. So I've got this guy. Comes over to A, comes over to B. You short it. I sub short circuit goes through this guy. And this 50K resistor that is still there, it behaves as if it isn't there anymore because we've shorted it out. So I'm going to draw it with a dotted line, right? Because electricity takes the path of least resistance. So if you short out this across these terminals, which is what we do for the method just says to do that. But if we do that, then this resistor goes away, which means that V2 will be 0, right? The voltage across this resistor will be 0 because there's no current in this resistor. All the current's going this way, right? All the current's going through the short, so the voltage in here becomes 0. So if that's the case, then on the other side, the diamond behaves as if it's not here. So that this doesn't have anything to do with the method, or at least I'm not drawing this because of the method. I'm not drawing this as a dotted line because of the method. I'm drawing this as a dotted line because of the effects of the method. All right, the method just says to short this out. That's what the method says. Method says leave the circles and short this out, and then you do that, and then there's going to be certain effects of that decision. You know, so if we do that, then this guy, because this guy is given by 4 times 10 to the minus 5th times V2. So if V2 is 0, then this thing, if V2 is 0, then this thing's putting out 0 volts as well, because it's a dependent source given, you know, V2 is 0, you're going to get 0. So the rest of the guys stay in there. They're hanging in there. Just this becoming a 0 volt device, it doesn't really affect the rest of these guys. They're still there. This is just behaving like it's a wire now, which for this particular configuration doesn't have any effect. Over here, this guy behaving, or this guy not only behaving, it is a wire, because the method says replace this with a wire. That makes this resistor go away. But here, making this kind of so we short this out because the method says to do that. That makes this behave as if it isn't there. Okay, the consequence of that is that this V2, the voltage across it, goes to 0, which makes this guy start behaving as if it's a wire. Now this guy behaving as if it's a wire, because of the way the rest of these elements are arranged, it doesn't change the way they're they're in there. It doesn't change their effect. Look, if this was here, if this wasn't here, it would. Like if this 1310 resistor, if this wasn't here in the original circuit, then this shorting this out would also, or shorting this out would short this out. Okay, but because we have this, they both stay. All right. So 500 microamps is still there. 100 ohms through 10. All right. Now what? This is 80 IB. I didn't write that in there. So if we had IB, we could get I sub short circuit, and if we had I sub short circuit, we could solve for R sub Thevenin, because we already have V sub Thevenin from the previous method. So we just need I sub B, which is up here, I sub B, and I can get that with current division, right? I have 500 microamps going into this node, and then it's splitting 2 ways, right? So I need I sub B, and current division will work. So IB is 500 times 10 to the minus 6, and split up by 1310 plus 100, and I put the 100 on the top because using current division, you put the resistor on the opposite branch on the top. And this is going to give me 35.5 microamps. Therefore, I sub short circuit this thing. I sub short circuit is just this current here with a negative sign on it, right? Because the arrow direction for I sub short circuit is down. That's just comes from our reference when we're using the method. That this method was derived with certain references, just like V sub Thevenin has a reference polarity, and so does I sub short circuit. So this polarity, this current direction, happens to be opposite of this. So basically, the I sub short circuit is negative 80 I beta. Okay, because 80 I beta goes around this way. So you need this negative sign to basically, correct for our reference current direction. It's similar to what we did over here, correcting for this V2 thing here. Similar. A little bit confusing, but you just have to deal with these kinds of things. So this guy works out to minus 80 times I beta, which is 35.5 times 10 to the minus 6 amps. So you end up with minus 2.84 milliamps is the way that works out. And we can solve for R sub Thevenin. Now R sub Thevenin is just by our method, by the short circuit method. It just says to plug these guys in there, so you get V sub Thevenin was minus 160 and I sub short circuit was minus 2.84, so you end up with positive 56.4 kilo ohms. And the answer, the answer is R sub Thevenin, which is 56.4 kilo ohms, and V sub Thevenin is it was negative. It was negative down here, negative. So the convention is the positive sign on the top, but I would have to list the negative value. So I'm gonna flip it around to so that I can use a positive 160 volts. And that's basically the answer here. I guess before we leave, we could, talk about the I sub short circuit method works, because this one's kind of easy to understand why it works. If you have a Thevenin circuit, then and if you shorted that out across terminals AB, if the convention is the positive polarity at the top for V sub Thevenin. So by KVL, whatever voltage is here at the source, all of that would have to be dropped across R sub Thevenin if you short this out. So basically I sub short circuit is running through R sub Thevenin, so it's just by Ohm's law. R sub Thevenin is going to be the voltage applied across R sub Thevenin over the current. So it's a little bit easier to understand why this method works than it is trying to understand why test source method works. Okay, test source method's a little bit more takes a little bit more thinking to understand. This one here you can kind of understand. Anyway, overall this problem is a little is a little difficult. There's a lot of funny things going on, but we can get through it fine, right? We did, didn't we? All right, hope this was helpful. See you next time.